Hello and welcome everyone to the DGDs for MAT1362, Mathematical Reasoning and Proofs. In these videos, which I plan to do throughout the semester, I'll be quickly going over the solutions to the exercises, and then during the live DGDs on Zoom, if you have any questions about these solutions or want anything explained in more detail, I can do that. But these videos will be here as reference if you want to review the solutions at any point. So, as we can see here, I'll be doing the exercises today from section 1.2, which I've listed out here from exercise 1 to 7. So let's just get into it. The first one is to prove proposition 1.7, which I've written out here. And it says that if a is an integer, then 0 plus a is equal to a, and 1 times a is also equal to a. Now these look very familiar if you remember the axioms of the integers. But let's first recall exactly what the axioms are. So let's recall. One of the axioms says that if a is an integer, then a plus 0 is equal to a. And this is the axiom of additive identity. Another one we have is that if a is an integer, then a times 1 is equal to a. This is the axiom of multiplicative identity. So even though these look like obvious statements according to this, they're actually not exactly the axioms. So in order to prove these new statements, we need to combine these axioms with another one, and that one is the various commutative axioms. So there's one that says if we have two integers a and b, then a plus b is equal to b plus a. This is additive commutativity. And another one, if a and b is an integer, then a times b is equal to b times a. This is multiplicative commutativity. Or we can also call them the commutativity of addition or the commutativity of multiplication. So, switching back to black to write a proof, what we're going to do is we're going to let a be an integer, because that's what we're reasoning about. And now we want to prove an equality, which means we can start with one side, make a chain of equalities justified by axioms that ends at the other side. So I like to start by writing consider. And we're considering 0 plus a, as of here. Now we know we can reduce it into a if we switch it to a plus 0, and we can switch it to a plus 0 using commutativity of addition. So this is equal to a plus 0 using, I'm going to write it this way this time, commutativity of addition. And this a plus 0 we know is equal to a using the additive identity. And this is then a full proof of that first equality. It starts on one side of the equality, ends at the other side of the equality, each step being justified by axioms. For the other equality, we can also consider uh, 1 times a. This is equal to a times 1 by the commutativity of multiplication. And that is just equal to a by the multiplicative identity. So we've also justified this equation. And that concludes the proof of this proposition. The second exercise is to prove proposition 1.18, which states that for an integer a, negative a plus a is equal to 0. Again, this looks very similar to something we have as an axiom, but let's recall what the actual axiom says. it says that if a is an integer, then there exists an integer called negative a, such that if we add a to negative a, we get 0. And this is called the additive inverse. This negative a is the additive inverse of a. And again, it's not quite the same. And just as with the last exercise, we can quickly arrive at a form where we can apply this axiom by using commutativity. So let's start our proof by saying that we're going to let a be an integer. Again, we're justifying an equality. So I'm going to start with this side and connect it to this side via a chain of axioms. So let's consider negative a plus a, just considering this left-hand side. This is equal to a plus negative a using the commutativity of addition, just as we were doing in the previous example. But this now is equal to 0 by the axiom of additive inverse. And so we've connected the left-hand side to the right-hand side, each step being justified by axioms. And so that concludes the proof. Exercise 3 is to prove the remaining parts of proposition 1.11, which I've listed out here. Part 5 is missing because it's proved in the notes, but we'll be giving a proof of these parts. Since these are a bit longer and they're going to use a lot of different axioms, I'm not going to recall the axioms anymore, but you can check them in the notes. So for each of these, it's an equality we have to verify, so our strategy is going to be the same. We're going to start by considering the left-hand sides and working our way via a chain of equalities justified by axioms to the right-hand sides. So let's start with number 1. First, we should let ourselves have some variables. So we're working with integers a, b, c, and d. So let's let these be integers. And let's consider the left-hand side of 1. A plus b times c plus d. We need to somehow start working it into this form. And if you remember maybe FOIL or the binomial theorem, you can see that this is just the multiplication of binomials. So we'd like to do that rigorously. And the way we do that is with distributivity. First, distributing a plus b into c plus d. So first of all, I'm just going to maybe write it like this as a bit of a reminder. We have a plus b. We're going to distribute the entire blue number across c plus d. So what we get is a plus b times c plus a plus b times d. And this is by distributivity. Get rid of this for now. Now that we have it in this form, we would like to distribute the c into the a plus b and the d into the a plus b, but the axiom of distributivity only applies from the left. So first we need to use some commutativity. So first I'm going to write it, I'll go in green now, c times a plus b plus d times a plus b. This is commutativity of multiplication, because this is a multiplication that we're switching the order of, and same here. And now again, we can use distributivity, and what we'll get is we'll get c times, oh, I am switching colors here. We'll get c times a plus c times b and that will all be grouped together because there is one pair of brackets here, so they should be maintained. And we'll get D times A plus D times B. And if we check what we're aiming for, we want AC plus BC. So those are just out of order. And we want AD plus BD. So these are also out of order. So we can just, sorry, this was distributivity. So now we can fix the order of these things by using commutativity of multiplication. It'll be 4 times. And we'll get AC plus BC plus AD plus BD. And this is commutativity of multiplication. And if you'd like to remember, we use commutativity of multiplication 4 times. So you can make a note that it happened 4 times. Here we commuted twice. So if it helps you remember, you can include how many times the axiom was applied. But the important part is that we're only using one axiom per line. We might use that axiom multiple times, but it's only one axiom per line. And in doing so, we've connected our left-hand side here to the right-hand side. So that is a proof of part 1. Part 2 is this here. So let's start by considering this expression. Like this. Now, the order of A, B, C, and D is not changing in any of these expressions. The only thing that's changing is the brackets are being put into different positions, and the axiom that deals with where brackets go is associativity. In this case, it'll be associativity of addition. So that's what we'll be applying. So the way I want to think about this is first as C plus D as just being one number. So I'm going to erase that. Give it a color. And now we have 3 things, and I want to use associativity to move the brackets from around the last 2 to around the first 2. So this is equal to A plus B, the first 2 things, plus the last thing, by associativity of addition. And already we have this, A plus B plus C plus D. So that gives us our first equality. Now to get to the second equality, we're going to do the same thing, but I'm going to re-bracket it slightly. Where are we going? We want A and B together. So we're going to think of it this way now instead. Yeah, we're just now instead of moving the black brackets, we're moving the blue brackets. We have 3 things. A plus B is 1, C is 1, and D is 1. And so we're going to move the blue brackets. And what we get is this. The blue brackets get moved to around the first 2 items. And the last item is left on the end. Again, this is associativity of addition. And just rewriting it once in black. We get what we were looking for. So there was sort of 2 equalities we had to verify. The first one is between these 2. The second one is between these 2. And we have all of them justified by an axiom. So that is the proof of 2. Now, 3 is that these expressions are equal. So you can see here the brackets are changing. Here B and C are grouped, and here C and A are grouped. So we're going to need some associativity. And we'll also need some commutativity because they're out of order. So let's start by considering A plus B plus C. A plus B plus C. Right. Now, we would like to get C and A grouped together. In order to do that, we have to get them next to each other. So let's say to get A and C next to each other, we could swap B and C, which we can do because they're within these brackets. So let's do this. We're rearranging addition, so this is by commutativity of addition. Now that A and C are next to each other, we can group them together by moving the brackets. And this is associativity of addition. Right, so we've got the things grouped together. Where are we headed? We're trying to get to C plus A in brackets plus B. Well, we already have B at the end. We just need to make this into C plus A, which we can do by changing the order with a commutativity. So now we connected the left-hand side to the right-hand side with implication or with axioms. So that is a proof of that equality. What does 4 say? For 4, it's very similar, but instead of addition now, we're using multiplication. In fact, it looks, I guess the brackets are in a different spot. So we're starting with A times B times C. And we would like to get to C times A times B. So we have to group A and B together. Well, they're already next to each other, so let's do that. This is now associativity because we're moving brackets, but it's brackets across multiplication. So this is associativity of multiplication. We would like to get to C in front, so we can swap that by commuting the C and the AB as one number. This is commutativity of multiplication. And then we're done. We got to where we wanted. C times, and then in brackets, A times B. So those are also equal. Lastly, we have part 6 to do, which is this expression here. So we have A times, I'm just going to write this one out so I just don't keep scrolling. A times B plus C times D. Is equal to AB times D, A times CD. All right, so this is what we'd like to show. So let's start by consider one side. Like this. Now, this A is multiplied by the B, and it also is sort of multiplied by C over here. So we would like to apply distributivity to make that happen. So let's apply distributivity within these brackets to get AB plus AC times D. That's by distributivity. We would also like to distribute the D, but distributivity, the axiom, literally only distributes from the left. So we would have to move the D to the left and then distribute. So to move it to the left, we can use commutativity. And now we can distribute. And when we distribute, there'll be brackets around the AB and brackets around the AC because they were multiplied first before the D showed up. So we need to keep track of that with the brackets. Now we just need to use commutativity of multiplication and associativity of multiplication within these pieces to reorder them to this. So for the first one, well, first I'm just going to swap the D's to the other side in both terms with commutativity of multiplication. Then the first one is fine, A times B times D. Here we just need to group the C and the D together, which we can do with an associativity. we started with the left-hand side. We have a chain of equalities justified by axioms ending at the right-hand side. So that is a proof of that, which concludes exercise 3. Exercise 4 is to complete the proof of proposition 1.15, which states that if you have two integers a and b which are even, then a plus b is also even, and a times b is even as well. A plus b case is done in the notes, so we'll just be focusing on showing that a times b is even. And so first, let's recall what it means to be even. An integer a is even if and only if there exists another integer, which I'm going to call k, such that a is equal to 2 times k. So the even integers are exactly the multiples of 2. So to prove this, we need to start with everything before the if. So all we get to start with is if a and b are even integers. So let's let a and b in Z be even. These are our assumptions. What does this mean? Well, it means we can apply the definition of even to them. This implies that there exists integers. I'm going to call them k and j. K is going to be for a, and j is going to be for b, such that a is 2 times k, and b is 2 times j. This is what it means for a to be even and b to be even. Now we'd like to know something about a times b, so let's just compute a times b. So now we can compute that a times b is equal to, well, a is equal to 2k, so we can replace it, and b is equal to 2j, so we can replace it as well. So this is just replacement. Now from here, we would like to rearrange this using the axioms into something that looks like 2 times an integer, because then we know it's even. So I need a 2 in front, so I'm going to use this one here, and I'm going to get it out in front by itself by moving these brackets like this. And when I'm moving brackets across multiplication, this is associativity of multiplication. And now we have that a times b is 2 times something, and we can say, note that k times 2j is an integer, since we started with integers, and the integers are closed under their operations of addition and multiplication. So what we've shown is that a times b is 2 times an integer. This means that ab is even. Exercise 5 is to prove proposition 1.17, which reads that if an integer a has the property that b times a is equal to b for all other integers b, well, not other, but for all integers b, then a has to be 1. So what we're allowed to use in the start of this proof, what we're allowed to assume, is everything before the comma. So we're allowed to assume everything in this green square when we start our proof. So while I've got green on, let's just unpack exactly what this means. So our proof would start with let a be an integer. We're not allowed to do anything to change or make any assumptions about a. It's just an integer that's chosen. So this is already chosen. I'm going to say it's specific, but unknown. And we have to show that it's actually 1. And what we get to use is that it has the property that we can assume that b times a is equal to b for all integers b. So now what does this assumption mean? Just unpacking it quickly. It means that for any b, we get an equation. So really this is sort of infinitely many assumptions, one assumption for each integer. So this looks like the assumptions that ... Let's say we come up from, well, let's go down so that it lines up. This is the assumption that 3a is equal to 3, that 2a is equal to 2, that 1a is equal to 1, that 0a is equal to 0, that negative 1a is equal to negative 1, that negative 2 times a is equal to negative 2, etc. It's all of these assumptions at once, because it's this equation for every integer. Because it's all of these at once that we get to assume, we can use any one of them. We don't have to use them all. So what I'm going to do is, for convenience, I'm going to use this one. So if we assume that b times a is equal to b for all integers, this implies that, in particular, 1 times a is equal to a. Sorry, not a. 1 times a is equal to 1. So this is something that we're allowed to assume, so we can start working from it. And what I'm going to do now is manipulate 1 times a using our axioms. So let's consider 1 times a. Now, we already did an exercise about 1 times a. If we go and check, we've already proved that 1 times a is equal to a using proposition 1.7. So we can use this proposition now since we've proved it. We can say this is, how do I want to do this? This is equal to a by proposition 1.7. And so now what we can say is now a is equal to 1 times a, and 1 times a is equal to 1. So a is equal to 1 times a, which is equal to 1. And so here we can apply transitivity. Let's apply transitivity of equality. And this therefore implies that a is equal to 1, which is what we wanted. Then a is equal to 1. So this assumption here, that this will work for all b, is a very big and powerful assumption. It's all of these. We don't have to use all of them. We found one that was particularly convenient, and using that part of this very big assumption, we were able to show that a is equal to 1. Exercise 6 is to prove proposition 1.23, which says that if we have an integer a and it satisfies the equation that a times a is equal to a, then a is equal to 0 or a is equal to 1. This part before the comma is what we get to assume. So let's start our proof that way. So let's let a be an integer and assume that a times a is equal to itself. Now, with nothing else except for these assumptions and the axioms, so we get to start from here and then use the axioms, we need to end up at the fact that a is equal to 0 or a is equal to 1. Now this we're going to do as a proof by cases, and it's a little tricky, but the way it's going to work is like this. So we're going to go by cases, which I'm just going to draw a quick sort of visualization of how this works. We're starting with the fact that a is an integer. This means that either a is equal to 0 or a is not equal to 0. So these are going to be our two cases. This is going to be case 1, and this is going to be case 2. And to prove in each case, we want to show the same conclusion. So we want this to imply that a is equal to 0 or a is equal to 1, and we want this to imply that a is equal to 0 or a is equal to 1. If each case coming from your starting point proves the same thing, then the starting point proves the thing, which is what we want to do. So this is kind of a depiction of our strategy. So we'll continue. So we'll proceed by cases. Where case 1, we can add in the assumption that a is equal to 0. Now, to get from the fact that a is equal to 0 to a is equal to 0 or it's equal to 1, we don't have to do anything. If it's 0, it's already one of the two that we need. So this implies that a is equal to 0 or a is equal to 1 immediately. So in this case, we're done. Now for case 2, we assume that a is not equal to 0. And since within this case, we're assuming that a is not equal to 0, we get to use properties of a or any axioms that refer to non-zero numbers. So what I'm going to do is start with the fact that a times a is equal to a. This is by assumption. By this assumption up here. And I'm going to apply an axiom, but just to the right-hand side. So let's just draw this in blue. The left-hand side is going to stay the same. And on the right-hand side, I'm going to write this as a times 1 using the multiplicative identity. Usually the multiplicative identity is applied to take a times 1 and turn it into a, but you can also go backwards. It says that a and a times 1 are equal, so you can use them in either way. Now what we have is an equation where it's a times an integer is equal to a times some other integer, and a is non-zero, which means cancellation applies. So a is equal to 1 by cancellation. And the cancellation here is in removing these first a's. Now if a is equal to 1, just as when a was 0, that means it's 0 or 1. If a is already 1, then it is 0 or 1. So a is equal to 0 or a is equal to 1. Which means now that starting from our main assumption, in case 1, we ended up at a is 0 or a is 1. In case 2, we ended up at a is 0 or a is 1, which means that this statement follows directly from our initial assumption, which means that this proposition is true. So we have completed our proof. Lastly, we have exercise 7, which is to prove proposition 1.24. And it says that for integers a and b, these identities are true. And they're identities about the additive inverse of elements. For instance, one says that the additive inverse of the integer a plus b is the additive inverse of a plus the additive inverse of b. Now, I'm going to prove 2 first, and then use it to prove 1 and 3, because having access to 2 makes the proofs of the other ones pretty easy. So let's start with 2. And to prove 2, I would like to use some propositions from the notes. So let's recall. I'll pull up the notes here. The first one is proposition 1.10, which is the uniqueness of the additive inverse. And it says, if a and b are integers, and a plus b is equal to 0, then b is the additive inverse of a. So this will come in handy. And we're also going to recall, oh, I want a P, not an R. Proposition scrolling through the notes here, 1.14, which states that if a is an integer, then a times 0 is equal to 0, which is the same as 0 times a. So we'll be using these two. Now the way we're going to use it is we're going to show that a plus something is equal to 0, which means that whatever we added must be negative a. So since we want to show that something is negative a, we're going to add this here to a. So I'm going to start by considering a plus negative 1 times a. Now I'm just going to use some axioms and these propositions to try and manipulate this into 0. So the first thing I'm going to do is replace a with a times 1. And doing that is just an application of the multiplicative identity, sort of in reverse. I'm going to commute this into a times negative 1, commutativity of multiplication. And the reason I did that was with the goal of using distributivity in reverse, to take this a out. So now that we've undistributed a, in the brackets here we have 1 plus negative 1, which we know by the additive inverse axiom is equal to 0. And so, using proposition 1.14, a times 0 is equal to 0. Which means now we've proved that a plus negative 1 times a is equal to 0. But whenever we have a plus something and it's 0, it means that that something is negative a. So this implies that negative 1 times a is equal to the additive inverse of a by proposition 110, which is what we wanted to show. We wanted to show that negative a is equal to negative 1 times a. I guess we have them in the other order here, but this is the same as this. So that's our proof of 2. Now we can use this. So let's now look at part 1. Part 1, we want to justify this equality. I'm going to start with the left-hand side, and I'm going to say consider the additive inverse of a plus b. This is equal to negative 1 times a plus b, and this is by part 2 that we just proved. So just like here we're using propositions that were already justified, if you justify something in part of a problem, you can use it in later parts. Now, we can distribute this negative 1. This is distributivity. And now that we have negative 1 times a, well, that looks a lot like this. And negative 1 times b is similar, but with b's instead of a. So this we can say is equal to the additive inverse of a plus this is the additive inverse of b. And this is, again, by part 2, which we've applied twice. So we've started at the left-hand side, and we ended at the right-hand side. So that's a proof of part 1. For part 3, we want to start with the additive inverse of a times b and end with a times the additive inverse of b. So let's consider the additive inverse of a times b. The same trick is we're going to write it as -1 times something using part 2. So this is equal to -1 times a, those were multiplied together, and then multiplied by b by part 2. Now we'd like to get this -1 next to this b so that we can use part 2 again to get the additive inverse of b. So let's first commute. Within these brackets, we're switching the a and the -1. This is commutativity of multiplication. Now we're going to use associativity to move these outside brackets. So instead of the first two things being multiplied, it's going to be the second two things. This is associativity of multiplication. And now we have -1 times b, which we know is the additive inverse of b by part 2. So we've shown that the additive inverse of a times b is equal to a times the additive inverse of b, as we wanted, which is all the parts, and therefore concludes the proof of exercise 7. So that's all the exercises. I look forward to answering any questions you have about these in the DGDs over the next 2 days. There's one on Tuesday, one on Wednesday. So I will see you there.